trickling in. Awesome. So, yep, recording just started. Sounds like folks are trickling in. We've just hit 10 o'clock. So I'll go ahead and get going here. This is the Manufacturers Roundtable on Industrial Heat Pumps. So welcome, everyone. Thanks so much for attending. This is sponsored by CETA, the California Energy Design Assistance. So I'm going to have Sean Williams go ahead and give a little background on CETA, and then we'll get into the webinar.
Oh,
I think you might be on mute, Sean. Still can't hear you, unfortunately.
How about that? Are you able to hear me now? I
I am
apologize.
indeed. Thank you.
Thank you so much. Well, thank you all for joining. Thank you all for having me to speak about the CETA program. So I'll just get started. So what is CETA? So CETA is California Energy Design Assistance Program. It's actually the only statewide utility incentive program for new construction and major renovation projects. And the purpose of the program is to promote innovation and decarbonization. CETA does work in collaboration with project teams to reduce demand, consumption, and of course carbon emissions. Through the program, we do accept the following project types: commercial, public, high-rise multifamily, industrial, and agricultural projects, granted that they are located in the investor-owned utilities service territory, as followed below on the screen there. Okay. Perfect. So why participate in CETA? So the top reason is you receive a complimentary decarbonization analysis that is tailored to specific project goals to help identify the most effective energy efficiency measures to implement. Great opportunity to gain analysis of some of the energy costs associated with various measures and their paybacks. Receive financial incentives to help offset cost of decarbonization measures, and of course, demonstrate a commitment to high performance building practices and design. Okay, so talking a little bit about the incentives here. So there is a $2,800 design team incentive. So this is per project, and it really serves as a thank you for participation. Right now, we are kind of running a little promo, if you will, where it's a $5,000. We're bumping it up to a $5,000 participation if we can get the project in before the end of the year. So this is specifically tailored to the design team that's working on the project. The second incentive is what we'd call a measure package incentive, and you can think of this as a rebate. So this is based off the actual measure package that the design team chooses, design team owner and developer alike, they choose to implement for their project. Okay, so just talking a little bit about high performance measures here. So CETA does aim to exceed California's decarbonization standards by identifying high performance measures and providing educational opportunities to explore use cases and best practices. Not only is it going to advance the market, but also qualifies participants for enhanced incentives through the program. So through our website, there is a list. It's under high performance measures. You can take a look at it. One quick note here for industrial projects, there are a few high performance measures out there, and it's listed as following. This is directly on the website. Alternate heating process design for industrial application, industrial heat pumps for process, thermal, water, steam, or simultaneous heating and cooling loads, microwave heating, and other drying technology. So if you all have a project that you would like to discuss, once again, my name is Sean Williams. I do perform outreach for Wildan and specifically the CETA program. So if there's any projects out there, feel free to take a look at our website, shoot me an email. Be happy to help. Thank you all.
Yeah, thank you so much, Sean. Again, really appreciate the sponsorship.
Absolutely. Thanks for having me.
So we'll get into this roundtable for today. So first off, we just want to talk why industrial heat pumps. Why are we having this roundtable in the first place? So industrial heat pumps are an awesome technology to help decarbonize one of the harder to electrify sectors, which is the industrial sector. We think of things like manufacturing, food production, other similar things in that vein. So with that, in today's roundtable, we'll discuss why are a growing number of industries embracing these heat pumps, and especially in Europe and Asia. What is the current landscape of the market for industrial heat pumps? Kind of what are the main barriers to adoption? So why haven't they necessarily been adopted heavily yet in certain places, including the US? And then what are some insights from retrofit projects and real world applications? So we're going to have definitely plenty of real world case studies from both Herman and Raj today. So very excited to get into it. I'll introduce our panelists right now. So Raj Ganaraj, he is a North America Technology Manager at Circular Thermal. He specializes in utility and energy engineering, driving innovation through the implementation of cutting-edge heat recovery and energy-saving solutions. We also have Herman on the call, Herman Robledo, who is the Industrial Heat Pump Sales Manager for North America at GEA. He started his career as a design engineer for General Motors, and he's worked as a Latin America sales manager, and he has also served as a sales manager for refrigeration, gas compression, and a sustainability sales executive. So both of them have deep experience in this sector. We're very grateful to have them on. With that, I'm going to stop sharing my screen and turn it over to Raj.
Thanks, Noah. Okay, can you see the screen?
Can do.
Okay, good morning, good afternoon to all. In this particular session, we are going to see about Armstrong International Heat Pump. Who's Armstrong International? And what's the difference between a heat pump and a chiller? Because when someone asks like how a heat pump works, we usually correlate that with a chiller. And what are a few applications where we can have a heat pump in an industry? What are the challenges in a heat pump? How we can overcome that when implementing a heat pump in an industry? And at last, we'll see like how we can identify whether a facility really requires a heat pump or not. What tool we can utilize to identify a facility whether really requires a heat pump or not. So to start with, I come from Armstrong International. It's a family-owned organization founded in 1900. We are more than 124 years old, thermal-based organization. We are experts in thermal utility optimization and management. We have 15 manufacturing locations around the globe. We manufacture high temperature heat pump, which generates 248-degree pressurized hot water, or it can be steam. Our minimum capacity is 0.15 million BTUs, and we can go all the way up to 7 million BTUs from one heat pump. We recently received a DOE grant to expand our hot water group facility in Michigan to manufacture industrial heat pump for US customers in USA. All our heat pumps are customized design. We usually say like, let the customer define what are the requirements they need in their facility, and we design the heat pump to match those requirements. Heat pump and chiller both works in the same working principle, vapor compression refrigeration cycle. Both have a similar components: compressor, condenser, expansion valve, and an evaporator. A chiller, for example, if it's a 100-ton chiller and it generates 45-degree chilled water, a heat pump can also generate 100-ton chiller and 45-degree chilled water. But on the condenser side, a chiller generates a warm water at 95-degree Fahrenheit, and whatever the heat from the condenser that gets released to the atmosphere with the help of a cooling tower. Whereas in a heat pump generates a high temperature hot water. This is just an example of 150-degree Fahrenheit. We can go higher than this. heat pump generates high temperature hot water. We can make use of this heating in a process heating or building heating. So if we use an equipment which generates heating and we put that in a proper use, we call the equipment as heat pump. If you're using chilled water, and the condenser water heat gets dissipated to the atmosphere, we call this equipment as a chiller. The heat pump compressor gets controlled based on hot water temperature. In a chiller, the compressor gets controlled based on chilled water temperature. The major difference between a chiller and a heat pump is that the chiller consumes lower electricity to generate 100 ton of cooling. Whatever the heat from the condenser, that gets wasted through the cooling tower. Whereas in a heat pump, it consumes more electricity to generate 100 ton cooling and also the heating from the condenser, and we are making use of it. The reason why it consumes more electricity is the compressor needs to do more work done. Then it can pressurize the refrigerant to a higher pressure. Then the higher pressure refrigerant would have a higher temperature, and it can heat the hot water to a higher temperature. So these are few differences between a chiller and a heat pump. When a customer asks us, we usually say that chiller is like a cold coffee, heat pump is like a hot coffee. Ingredient remains the same. At what temperature we are consuming it makes a difference. Anyone who operates a chiller can operate a heat pump. Whatever the maintenance required on a chiller, same thing is applicable in a heat pump as well. So how we can integrate a chiller in a running facility? So imagine a facility is having like 400 ton chillers, which pretty much runs throughout the year. Just an example, that generates 45-degree chilled water that goes to the process cooling. It comes back at 54-degree Fahrenheit. It runs in a common header, and that goes back to the chiller. If this facility requires, say, 2 million BTUs of heating capacity at 150-degree hot water, we have designed a heat pump. For a heat pump to operate, we need some source on the evaporator, some waste heat source. So in this application, we are taking the chilled return water, which comes in the return header, slip a small stream of water at 54-degree Fahrenheit, let it go to the evaporator. The heat pump, since it generates cooling, the 54-degree Fahrenheit drops down to 45-degree Fahrenheit, and then we can put back in the same header. The primary purpose of having a heat pump is to generate high temperature hot water. Since it works in a refrigeration principle where we would get simultaneous cooling, if we integrate that with the chilled water network, we can contribute some sort of cooling in the chilled return water loop so that instead of 54-degree Fahrenheit going to the chillers, now it will be lower than that because heat pump evaporator contributes some sort of cooling here. If the cooling load from the heat pump evaporator matches with one of the chiller, then the chiller can be switched off. When a chiller gets switched off, it's an electrical equipment. Whatever the power consumption by the chiller is saved, the condenser, water circulation pump power consumption can be saved, the cooling tower fan power consumption can be saved, whatever the water losses from the cooling tower, that can be saved. Having a heat pump to generate hot water, if that is integrated with the chilled water network, we can see a cascading savings in the chiller room. So one of the major reasons why the heat pump became famous because it can do simultaneous heating and cooling, and customer can see many benefits in their existing cooling process. But this comes with a certain challenge. Imagine a facility, they are operating chillers, all 4 chillers during summer, but not during winter. If there is no load on the evaporator, the heat pump will not run. So it's very important to ask customer, how many chillers you operate during summer, how many chillers you operate during winter, what is the minimum recorded chilled water temperature, so that we can take that as a basis for the design. So the heat pump would run during very low temperature in the return and achieve the set point. If there is no load on the condenser, the heat pump will not work. So we need to find the right balance between the source and the sink and then design the heat pump. Customer can ask for 2 million BTUs of heating, but if there are no chillers going to operate during winter, the heat pump cannot run. So we used to ask like a lot of details from customer and then design the heat pump and deliver it to them. The very common application of integrating a heat pump and chiller is in pharmaceutical facility where their process requires heating and cooling, and air handling unit requires heating and cooling to maintain certain temperature and humidity in the room. So a heat pump can be designed and the hot water or hot glycol can run in closed loop heating, and the chilled water can be utilized as a waste heat source in a heat pump to generate simultaneous cooling and heating. The heat pump performance is calculated based on a very simple formula called coefficient of performance. What is the electricity we feed to the compressor and what is the heat output we get out of it? So if I feed 200 kilowatt of electricity, we can get about 560 kilowatt of thermal heating. The heating COP becomes 2.8. In a heat pump, we can make use of the cooling as well. So it is called as combined COP. If I feed 200 kilowatt of electricity to the compressor, I can get about 560 kilowatt of thermal heating and then 360 kilowatt of thermal cooling from the same machine. So the combined COP becomes 4.6. This COP differs based on source water temperature and sink water temperature. This is just an example to explain what is a COP. So in other words, if I spend $1 worth of electricity in a compressor, I can get about $2.8 worth of heating and $1.8 worth of cooling. Now, before we go too much detail with customer, we usually ask what is the electricity cost, gas cost, what is the source temperature, sink temperature, and then we quickly calculate the efficiency of the machine by comparing it with electricity and fuel cost. So by taking a formula and put the electricity cost, fuel cost multiplied by if they are generating hot water with the help of steam boiler, what is that boiler efficiency? And if that is lower than COP, when customer is going to replace their steam-based hot water system with a heat pump, they would see some sort of savings. But if this calculation is going to be higher than COP, then heat pump would operate in that facility. But in order to operate it, customer need to pay more money to operate that heat pump. So we do this calculation and tell customer that whether it is going to fall under positive operating cost, negative operating cost, what is the savings, and then customer can decide and implement this heat pump technology. The other common application in light industry like food, pharmaceutical facilities, if they have an air compressor and that is water cooled with the help of cooling tower, whatever the waste heat from the cooling tower, before it goes to it, whatever the waste heat in the cooling tower water, that can be directed to the heat pump. So the heat pump can cool it from 95 to 86 degree Fahrenheit. On the other side, we can generate high temperature hot water up to 175 degree Fahrenheit. This is a very common application we have seen in most of the light industry, how to utilize the waste heat from the cooling tower water and generate high temperature hot water from the heat pump. The other common application in most of the pharmaceutical facilities or in the research labs, if they have an air handling unit, they bring in 100% outdoor air, they condition it, that goes to the room, and there is a centralized exhaust which takes the entire room air and throw it out at 70 degree Fahrenheit. We can have a heat recovery coil, recover the waste heat from it, use that in a heat pump to generate high temperature hot water that can be used in the same hot water coil in an air handling unit, or it can go to a process heating, or we can put back in the centralized hot water loop. So this is another common application where the waste heat is very consistent throughout the year, and we can make use of that waste heat in the heat pump to generate high temperature hot water. We manufacture high temperature heat pump which generate hot water all the way up to 248 degree Fahrenheit. We have few installation. The very common application we came across is integrating a heat pump with the dryer. So any food product dryer, if that exhaust is say like 140 degree Fahrenheit and above, we can have a heat recovery coil, a fin tube heat exchanger or like a radiator coil, where the warm air goes across the fin tubes. There is a water loop which extracts the waste heat from the exhaust air before it gets released to the atmosphere. We can make use of the waste heat from the air and put that as a waste heat source in a heat pump, and heat pump can generate 248 degree hot water. It can run through another fin tube heat exchanger where it heats the fresh air, the fresh air or the return air to 230, 240 degree Fahrenheit. And that goes to the dryer and removes the moisture from the product and dries the product. So this kind of a setup extracts all the waste heat from the air and feeds to that heat pump, and heat pump feeds the heat, high grade useful heat to the dryer. So initially during the startup, they may need to start with a gas a fire heater or like an electrical heater until the exhaust comes to 140. After that, this is a self-sustained unit that the waste heat goes out, heat pump captures it, heat pump system captures it, and then it feeds back to the dryer. So if it's like an 8-hour batch, first 20 minutes, probably a gas-fired heater would be on or an electrical heater would be on until the exhaust comes to 140. And then the remaining 7.5 hours, the heat pump takes over the heating process. We can make 248-degree pressurized hot water. And if we flash that in a flash vessel, we can generate steam close to like 5 PSI or up to 10 PSI of steam. That is easily possible. All we are doing is that taking the pressurized hot water, flash that in a flash vessel, and we can make a steam. If we can put a bunch of MVR in series, we can take that pressure from 10 PSI to a higher pressure. But depending on the source temperature, what we use in the heat pump, if the source temperature is very low and we are generating steam, the COP of the system would come close to 2 or even lower than 2. With an electricity and gas cost over in US, if the electricity to gas ratio is greater than 3, for example, and if this is going to generate steam and the COP of the system is 2, it will not be viable for customer to implement it because they need to pay more to operate the system. The system could work, but the operating cost would go higher. So making steam is possible by just flashing the pressurized hot water to a lower pressure, and we can make steam. Some of the common requirements in an industry is that customer wants to replace their steam boiler with the help of a heat pump. So we get common inquiries like, can you give 100 PSI of steam heat pump? We can do that. We can generate 248-degree hot water, flash that in a flash vessel. We can make 10 PSI of steam, have steam compressor, multiple steam compressor in series, and increase the steam pressure to 100 PSI. Whenever customer define a steam heat pump, they do not give their process details. Not necessary that every customer shares what their process details are. So when we get an inquiry to replace a steam boiler with a heat pump, then in this case, the CapEx goes higher because there are a lot of equipments involved. There are a lot of electrical equipments involved because the steam compressors are electrically driven. So the CapEx goes high, the savings goes lower because the operating cost is very high in this case. When customers see this and they say like it's really not implementable, then we ask customer like, where do you take this 100 PSI to? They say that they have a pressure reducing station right near to the point of use and they are reducing it to 30 PSI. Okay, let's go for a system of 30 PSI steam heat pump. Same setup, instead of 3 steam compressor in series, just 1 steam compressor in series, and pressurize this 10 PSI flash steam to like 30 PSI of steam, and customer can use it. Even then, it's not readily implementable because the CapEx is still high. The savings has got a little bit better because there are few electrical equipments in the setup, but still if customer is not ready to implement it, then we ask customer like, you do not really have to share your core process, but at least tell us where do you take this 30 PSI and use it. So they say like, we take the steam, put that in a steam heat exchanger and heat the process liquid to 158 degree Fahrenheit. Now, to heat a process liquid only to 158 degree Fahrenheit, do they really need steam? Why can't they go with the steam, a hot water heat pump, generate high temperature hot water, redesign the heat exchanger from steam to hot water, the surface area is going to go big, and heat the water to 158 degree Fahrenheit. In this case, there is only one equipment, so the CapEx is low, the operating cost is better, so the savings got better, and this is more implementable for customer. Now, when customer is okay with this, and then when we go for a walkthrough to find a place for a heat pump where this needs to be installed, during the walkthrough, we see an equipment, thermal oxidizer, which throws a high grade waste heat in the air. Now, if this heat pump is going to be like 100 feet away from this equipment, do we really need a heat pump? Why can't we recover the waste heat from the exhaust and use that in the heat exchanger to heat the process liquid to 158 degree Fahrenheit? Do we really need a heat pump in this facility? If we have enough capacity which comes out of it, and if we can recover the waste heat and use that in a heat exchanger, we really do not need a heat pump. So how to identify whether a facility really requires a heat pump or can they do a direct heat recovery and live without a heat pump in a facility? So in order to do that, we follow a pinch methodology or pinch analysis, where we collect few data and see where the direct heat recovery is possible and where heat pump is really required. So in order to do that, we collect data like, what are the hot heating requirements in a facility. So in x-axis, you can see the heating requirements in million BTUs and the temperature in the y-axis. So we identify what are the process which requires heating. So for example, this is process A, which needs to be heated from 60 to 100. Process B, which needs to be heated from 100 to 140 to or 3 million BTUs of heating capacity. So we measure what those heating requirements are in the facility, plot that in a chart. Currently, all the heating could be done with the help of steam or maybe a gas-fired heater in the plant, and that's how they operate in the facility. Because of decarbonization measure, if customer plans to go for a steam heat pump, that is still possible, and use the same steam infrastructure and generate steam and put that in the header and still do the heating. But we just saw that a steam heat pump, a COP is lower when compared to a hot water heat pump. So in the same facility, instead of going for a steam heat pump, if we go for a lower temperature hot water heat pump to heat a process from 60 to 100, a medium temperature heat pump to heat the process water from 140 to 160, a high temperature heat pump to heat from 180 to 250. These heat pumps will be more efficient than the steam heat pump, but we need to change the steam infrastructure to a hot water infrastructure. If we can do that, these machines would operate at a much higher efficiency than a steam heat pump. The next analysis we do is, what are the processes which requires cooling? Say, for example, process D requires cooling from 230 to 210, and that is done with the help of a cooling tower, or the low temperature process cooling is done with the help of a chiller. So we plot what are the process which requires cooling in the same facility. And then we combine both in a chart, and a point at which where the heating requirement and the cooling requirement meets, we call that as a pinch point. And above the point and below the point where the curve overlaps, we can do a direct heat recovery. For example, a process needs to be cooled down from 230 to 210. We can extract the heat from this and heat this another process from 160 to 180 with the help of direct heat recovery, maybe a plate heat exchanger or a shell and tube heat exchanger. We do not need any electrical requirement to run a heat pump to do this, or electricity to run a cooling tower to do this. Maybe a electricity requirement for a circulation pump between the plate heat exchanger to extract and recover the heat on the other side. So above and below pinch point, we can do the direct heat recovery. So what left out is the remaining low-grade waste heat and a high-grade heating requirement in the facility. So this is where the heat pump comes into a picture. A heat pump can move a low-grade waste heat, can convert into a high-grade useful heat, and we can put back in the same process. So we have optimized many equipments in this process by doing a direct heat recovery and implement where the heat pump is really required. This is a very, very ideal situation in a running plant, not necessary that every plant operates this way. Imagine this particular process D is in northeast corner of a plant, and this process is southwest corner of the plant, and there are miles apart. And if customer is not ready to lay down the pipes from one corner to the other corner to extract the waste heat and make use of it, if it's not practically viable, then this heating and cooling should be done by conventional methods. But if they are nearby, we can certainly extract the waste heat and utilize to heat a specific process and optimize the thermal requirements in the entire facility. So this is how we can identify where direct heat recovery is possible, where we need a heat pump in the facility. We do this analysis, this kind of pinch analysis at many different customer sites. So in this particular curve, this is the process which requires cooling. This is the process which requires heating. There is no pinch point here. So all the heating for that particular industry should be done with the conventional methods or by heat pump or any other technology. But this facility requires, in this particular facility, we cannot do any kind of a direct heat recovery. But this is another case study where there is a pinch point, and above and below the pinch point, we can do the direct heat recovery. So the remaining of the heating requirement in the facility can be done with the help of a heat pump or any other technology. this is another case study where we have a pinch point. Above one pinch point, we can do the direct heat recovery. In this facility, there are a lot of exothermic reactions. So there are a lot of waste heat in the facility. If we can directly recover it, we can do all the heating requirements in the industry with the help of direct heat recovery. In this facility, they do not need a heat pump. In this facility, a combination of direct heat recovery and a heat pump, but this facility does not require a heat pump. So we educate customer that if they come with an inquiry for a heat pump, not necessary that we have to do always pinch analysis, but we always ask, like, do you have any other high grade waste heat which is nearby and we can make use of it? Probably if there are few million BTUs of waste, heating requirements still needs to be done. After doing a direct heat recovery, that can be done with the help of a heat pump. So that's how we educate customer when they come for a heat pump inquiry, that at least have a pinch mindset to evaluate before you go for a heat pump implementation. So yeah, that's all I have from my side, Nova.
Raj, thank you so much. This was excellent. Really appreciate you explaining the difference between heat pumps and chillers and getting at the pinch analysis and when a heat pump makes sense. I think I'm gonna have a couple questions from the Q&A right now. So there was a question, what is the refrigerant in Armstrong heat pumps?
We use synthetic refrigerants, HFOs, R1234ZE for a medium temperature heat pump up to 194 degree Fahrenheit. For 248 degree Fahrenheit, we use R1233ZD as a refrigerant, which is having a GWP of 5. And it falls under A1 category. It's not toxic, less toxic and less flammable nature. That's what A1 category are. So we leave the choice to the customer whether which refrigerant they would like to go with based on their hot water requirement in their process.
Awesome. And then one more here. What is the typical max lift that the heat pump compressors can handle?
Okay. There are two types of compressor we use. One is reciprocating compressor. If you have chilled water as a source, say for example 50 degree Fahrenheit, and you would like to generate hot water all the way up to like 195 degree Fahrenheit, a reciprocating compressor can do that, but it comes in a smaller capacities. But reciprocating compressor can do it. If it's a screw compressor, you have a 100 degree of waste heat and you would like to take it all the way up to 248 degree Fahrenheit, a screw compressor can do that lift, and that comes in a higher capacity, and screw compressor have a very good turn down. So those are the temperature lift with respect to the selection of compressors or the type of compressors.
Excellent. Thank you again, Raj. Really appreciate it. And there are a couple more questions, but we might return to those at the end if we have time. Herman, I'm going to turn it over to you. So Raj, if you don't mind, stop sharing, and then Herman, you can go ahead and take it away with your slides.
Okay. Do my presentation.
Great, looks good.
Okay. So my name is Germán Robledo. I'm the Industrial Heat Pump Sales Manager for GEA or GA Heat Pump Technologies. We're a company that had 5 business units, most into the process equipment, like we are in the food and beverage, breweries, dairy, sodas, bakery, anything as far as far as food, also and drinks. Also, we are in the gas compression, oil and gas, anything regarding like turbines, gas wells, renewable gas energy, landfill, biogas, and stuff like that. We are part of the company where we make compressors. Those compressors goes into a lot of food and beverage companies making refrigeration systems. And by default, now they're asking for the heat pumps, and now we're making heat pumps with these compressors. So we are a compressor manufacturer. We make screw compressor technology, and we make piston compressor technology. We are not into the scroll technology or centrifugal technology, only the piston and the screw. So heat pump is something that is becoming very new into the US. Heat pumps are old. They've been there for years. Unfortunately, the low gas prices in the US really didn't help that much to sell heat pumps in the US. But now it's making a lot of sense, business, because people are setting these decarbonization targets, companies are setting anything like for 2040, 2050 and beyond, right? So what's going on this is that when you look at that, the Department of Energy came with a publication in September of 2022. They call it the Roadmap of Decarbonization. It's a good publication to read, but basically it's telling all the industry 4 pillars or 4 steps how to get into decarbonization, basically on your Scope 1, Scope 2, and Scope 3. Scope 1 is all related to your direct emissions. Scope 2 is indirect. It's basically the source of your energy, and where is a wind turbine or a solar system or the typical gas turbine or typical coal turbine or hydroelectric. Scope 3 is more difficult to assess. It's everything related or associated. Like when you travel and you rent a car, are you renting a car that's still using gasoline, or are you renting a car that's using an electrical vehicle? So things like that. So on that aspect, they go and tell you that you need to make 4 steps. Energy efficiency. It's like what you have today. Go and take a good look at it and see if you can make it better, improve it by making more temperature changes. Maybe you don't need those low temperatures or high temperatures in reality. They were there probably for the safety factor. Maybe you can start cutting them down and probably make things more efficient by new heat exchangers, clean heat exchangers, do the whole pinch analysis theory of recovering heat. So it's anything that you can do today without spending too much as far as energy efficiency. The second one is industrial electrification. Is basically to replace any heating by combustion, replacing any heating that is done today where you make steam and steam goes through a pipeline and going to a heat exchanger and it's making hot air or making hot water, to replace it now with some electricity technology. Could be microwave, could be induction, could be arc, could be something else. That's where the heat pump falls in place. The other two is basically the low carbon fuels energy sources, is to replace any gas, natural gas on your boiler by hydrogen or biomass or any new technology that is coming today. CCUS is the carbon capture, utilization, and sequestration and storage, is to capture those emissions. Think of a way of putting them somewhere to storage them. If you think you have a need for them or use for them, you can use them. And if not, inject it back to the earth, right? So ideally, you start with nothing, and then you start putting these steps gradually through time in your industry. And ideally, if you start incrementing them per year, then ideally you get up to 2050, 100% carbon neutral. So there are different heat pump technologies. One of them is called closed cycle. It's basically where a lot of people are, like me or myself or my company. It's basically compressors. It's basically anyone that makes compressor and is compressing a refrigerant. That's what they call MVC. Heat activates the absorption cycles. There is not a compressor, but there are heat pumps that they use absorption cycles. Some of them are more famous in Europe than in the US, but you can use absorption cycles for the heat pump. And then the open or semi-open is basically to make steam. You make steam at a low pressure, and then you recompress it and raise it out in pressure via some mechanical device. It maybe was something they call vapor fans. Some people have steam compressors. So it's in a way, all of them are heat pumps because you're raising the temperature levels that you need. So a heat pump becomes really a game changer in the industry. It's an opportunity for a lot of efficiency, a lot of savings, and it's the low-hanging fruit. So if you look at all industries, they have different thermal needs. They have heating, so they do steam and steam goes and heat waters or heat airs. They can do it for pasteurization, cleaning in place, for washing, for distillation, for drying, anything where they need heat, energy that comes into the process. Same time, a lot of these industries, they need by process or by product to remove energy, to remove heat. So we call them chillers, we call them refrigeration systems. So basically, it's a way of removing heat out of the process, out of the product. If you think for a moment, you have the same temperatures or sometimes the same things, but at different levels. The idea is to combine them and see how you can take that heat out of the boiler and do it with a heat pump. You will never replace boiler in a way you probably need to continue using the boiler. So the heat pump has been a lot of explanation, technical around it. It's basically a compression cycle. You're going to compress a vapor or a refrigerant or gas, whatever you want to call it that way. But it's a way of comparing two energies, combustion energy versus electrical energy. Combustion is basically the fossil fuel boiler, natural gas, bunker, diesel, whatever you're burning in that boiler, even biomass, and you're making heat, you're producing heat, and you send it to your process. Heat pumps don't make heat. Just something to make clarifications. Heat pumps move heat, they don't never make heat. You need a heat source. You need a way to capture heat from somewhere else and move it through the heat pump. So boilers make heat, but heat pumps don't make heat. The benefit of the heat pumps is that it can provide a cooling benefit because it's a compression cycle. So you have an evaporator and you have a condenser. On a chiller, you focus on the cooling benefit, the evaporator. On the heat pump, you focus on the condenser, the heating benefit. So you can focus on both of them at the same time with a heat pump. So the efficiencies is basically related to heat source. You can have air source heat pump. Some people call them ASHP. You can have water source heat pumps, WSHP, ground source or geothermal, GSHP. Industrial waste many times is a water source heat pump. And any other type of heats. We see heats like from car industries. We see heats from building space. We see heats from chemical sectors. We see heats from oil and gas. We see heats even from landfill. So it's anything that where you have some heat. Basically, you bring that heat source or that, call it fluid, into the heat pump, and you need to cool it off, like cooling water. Cooling goes to a water cooling tower, gets to knock off that heat, and now you have cold water, it goes back to the process. Now your heat pump is your cooling tower. Condensers, the heat of rejection of the chiller goes to a condenser. It's rejected to atmosphere, you cool and change phase that refrigerant into liquid and send it back to the process. Well, your heat pump becomes your condenser. So you have that chiller that is called like a floated type chiller where you have the heat source, and now you have a compression cycle and add different heat exchangers to capture heat sources available from compressing a gas. Some of them will be called superheating. That's taking off the sensible heat of the gas. Condenser is taking the latent heat of the gas, and subcooling is taking the sensible heat of the liquid refrigerant. So there's a lot of technologies, proven technology, commercial technology today is able to make up to 95 Celsius to 203 F water. There's a lot of cases already conventional for the residential space, commercial space, and now industrial. 95, and we make with ammonia, we can make up to 95 Celsius, 203 F water, leaving out a heat pump with ammonia. If you're going to go higher than that, like the steam level, some of them are seen in the prototype, and some even higher level, let's see in the lab research. There are a few cases that are already on the high level on the yellow zone, but there are not cases in industrial on the red zone, whether in the US or in Europe. It's more on the lab research, a lot on universities and testing. The criteria for the heat pump is the COP, coefficient of performance. Basically, you're comparing your performance of the boiler, which is 80%, 90%. Electrical boilers will be 95%, and electric boilers 98%, versus a compression of a refrigerant. Based on the nature of that refrigerant, you can get a high efficiency. Ammonia by default is the highest, the best refrigerant so far, whether on cooling or heating. So it's the highest COP that you can get from any refrigerant. You can go on the synthetics, chemicals, like HFOs or HFACs or whatever, like in this scale that you can see down here. And they can get some temperatures, but the COP is really lower compared to naturals like ammonia. Hydrocarbons is another refrigerant. You can get some COPs as well. But also ammonia is always the highest. CO2 is another one. It's on the bottom chart because they are not really great as efficiency, but you can use them because regulations or limitations. You design heat pumps regarding that refrigerant, and you design it around your compressor level or design pressure level. The higher the temperature, the higher the pressure. That's going to impose limitations on your compressor technology. You can get up to some level of pressure because of the compressor manufacturing. Many compressors manufacturers have compressors available up to 900 pounds. So that's the limitation on compressor technology. You want to go higher, then you need to find another technology. Some compressors can get into higher pressure, but that will be like those centrifugal or turbo machinery or turbo compressors. A couple of manufacturers made them, so we call them turbo compressor or turbo centrifugal compressors. And with some refrigerants that you can see on here, is some will do hot water temperatures, and then if you go to steam, you look at this chart, which we call that the critical point, the critical temperature. That's the maximum temperature that you can get out of them. So you can see on the chart, none of them can get up to 200 Celsius, only water. That's the reason you make steam and recompress steam. But most of them stop around 160 Celsius, which is 320 F. So if you're thinking at higher temperatures, maybe you need a hot water heat pump combined with a steam heat pump, and then probably to find something else to get into the 200 Celsius. So technology-wise, nothing is out there yet to make 200 Celsius without a heat pump. Has to be combinations of technology. So the efficiency is the comparison how you do it in the process. Boilers by default have an efficiency of losing energy. You got 80%, you put X amount of units of fossil fuel into a boiler, but you get less units of heat outside the boiler. The heat pump is the whole different game. You get free units, that means waste heat that you capture and move it into the heat pump, plus the heat of compressing that gas, and it becomes the same unit that probably you get out of the boiler or even more than that. But the efficiency is related that the boiler is able only up to 80%, where heat pumps you can see 300%, 400%, even 1,000%, and even 10,000%. So we call it COP, coefficient of performance. There are different types. We call it COP, COP Carnot, COP Gustave de Lorentz, but industrial commercially just go COP. We call it line because you need to account all the motor losses, the starter or variable frequency driver losses, and any other electrical component losses. So you don't look at the COP shaft, you look at the COP line. So the higher the temperature, the lower the COP. The lower the temperature, the higher the COP. The higher the capacity may impose on reduction of COP. The lower the capacity may help you to get a high COP. So when we look at COP, there are different ways of looking at this, but these are real cases that we've seen in the US. And just to give you an example on this, basically, if you need a capacity of 1,500 kilowatts, that's around 5,000 MBH, BTUs per hour, right? You need a boiler that is 80% or coefficient 0.8, and you run 18 hours a day, 6 days in the week, 50 weeks in a year. That's a total of 5,400 hours per year. For the boiler to make this 1,500 kilowatt need, you need to consume around 1,800 kilowatts. That's a total of 10 million kilowatts per year. If you get a heat pump that for selection purposes and everything gets in a COP of 3, that's 300%. Heat pump only needs to consume 500% kilowatts. Now you can see why heat pumps make sense. It takes less energy to make the same heat. So a heat pump is going to consume around 2.7 million kilowatts per year. These are some prices given to us by customers where we already make some cases, sold cases of things like that. You got Texas, Nevada, California, Colorado, and Idaho. Basically, your price for kilowatt, your price for natural gas, these two columns where you look at it as a price for BTUs or price on kilowatts. And you have something that we call the spark gap or spark spread. It's a ratio of dividing the kilowatt price based on the natural gas price. You take your boiler operation per year, this 10 million, multiplied by your price of natural gas. You take your heat pump operation per year, multiply that 2.7 million per the natural, the price on kilowatts, and that's the money you'll be spending per year if you use natural gas to make this heat or heat pump or electricity to make heat. Say that a heat pump comes around $800 per kilowatt, so 1,500 kilowatts multiply 800 gives you a total investment of $1.2 million. You take that investment, divide it by your difference on this energy, and it takes you the paybacks of return on investment. Worst case here, you're looking at 14 years, 23 years, and it's all related between efficiency of the heat pump and spark gap. The reason you see the worst years is because the spark gap is very close to the efficiency of the heat pump. The one that is really far out from the efficiency of the heat pump, like 1.5, is one of the best cases. So the rule here is that you got to have an efficiency higher, at least 1 point higher than the spark gap ratio. One way of scoping test of this is that if the heat pump gets about a 3.0 efficiency, take your gas boiler, divide that efficiency, and it gives you efficiency of ratio 3.7. Your spark gap is below that 3.7, you're going to make some savings in your utility costs. If it comes equal, there's not really some savings, just break even. And if a spark gap is higher than that, you're spending more money on electricity than gas, so probably not a good case for a heat pump. If we move the heat pump to an efficiency of 4, now you can see right away that the years that we were looking at now went down. The guy that was around 20 years, well, now it's 10. And the guy that was 23, now it's 14. And the other guys even start cutting more your paybacks. And also the consumption of energy on the heat pump is less. That's the reason it's improving in efficiency. So the takeaway of this, and that will be the next slide, if we go to an efficiency of 5 is even better than anything, and 6 is even better. So the idea is to find higher efficiency on the heat pumps. Reason you need to find a high manufactured or high compressor technology or refrigerant, but also many times we see customers that they want to cut down the amount of money they want to spend on the heat pump. They don't want to really go high. So when they see that targeting for a high capacity or targeting for a high temperature is very expensive, well, we tell them in order to get a high efficiency instead of a low efficiency, start targeting your heat pump to a low temperature or to a low capacity, wait a couple of years, 2 years, 3 years, 4 years, and if results are so great, then buy the second heat pump for the missing temperature or the missing capacity. Now, when it comes to the market, there are different technologies. We are a technology of piston and screw. We can start industrial-wise. People call things in kilowatts, but if US is about BTUs, you can see the scale in BTUs. Commercially wise, many people say that industrial start around 100 kilowatts. Some other manufacturers may say that industrial start around 1,000 kilowatts, which is 1 megawatt. And other compressors manufacturers may say that real industrial start around the 10,000 kilowatts, 10 megawatts. So we develop different capacity levels from 100 kilowatts up to 10 megawatts in one unit. And we can reach up to 95 Celsius or different temperatures depending on compressor technology. And if it becomes really high than that, like 20 megawatts, 40 megawatts, it becomes multiple sets. You start putting 2 heat pumps, 3 heat pumps, 5 heat pumps to make up for the capacity. And then you lay out what we call a single stage. There's one source, one compressor. But if your temperature's difference between heat source and heat sinks is way too high, then you become a 2-stage, 2 compressors. One compressor goes from the low to an intermediate, and the second compressor goes from the intermediate to the highest. So the heat pump is just like a chiller, but now you're adding heat exchangers. You're adding more. You're adding the superheating. You are adding the subcooler and a condenser and evaporator. Everything is mounted by the manufacturer. Everything is pre-piped or piped by the manufacturer. All these things are supposed to come with a low charge refrigerant to make it really nice that you don't have to use a lot of refrigerant inside these systems. All of them may be coupled with a variable frequency driver. So you may mount the driver or start it on the skid. You can change the dimensions of the skid based on the space restrictions or anything that you have in your system, right? And you can have all 4 heat exchangers or only 3 heat exchangers or only 2 heat exchangers. Not all applications would require a superheater. Not all applications would require a subcooler. And that's going to drop the price on the heat pump. So heat pumps basically is taking heat from many industrial places. A lot of them are refrigeration or chillers. Today, you're sending that heat to condensers or cooling towers. Well, the heat pump becomes one of replacing that condenser or replacing that cooling tower. So you stop using them. Now you start having water savings. The heat now start going to the heat pump, and heat pump can return things to your chiller or refrigeration system or application. Also, in a way, the heat pump, you can look at it as a condenser or as a cooling tower. To decarbonize steam is a big question. The big thing that we see in the US is for years, as the technology has been around, is to make steam be a fossil fuel on a boiler, and steam goes and make hot water. But one of the issues, and it's recognized, is that steam is probably not the best technology around, but it's what has been available. You know, fossil fuel is cheap. It's cheap to handle, cheap to storage, and cheap to burn. That's the reason heat pumps has been difficult to compete. But now people are thinking on decarbonization, you know, climate change and other metrics they want to do. So there's going to be a way to decarbonize steam. The thing that happens in many plants is that they want to replace steam by hot water, and it may become very expensive to retrofit the steam pipes, the steam heat exchangers now to hot water pipe, and hot water heat exchangers may be an added cost. So some people are looking for steam, and there are processes where you really need steam. So that's where you need to go back and see that there's heat pump technology to make steam, the MBRs, the steam compressors. Basically, hot water comes to a heat exchanger that runs on vacuum, negative pressure. So you're just changing the boiling point for water. It's running at a lower temperature than the boiling point. And now water flashes, becomes steam, but it's a low-grade steam. It's a low-temperature steam. And then you raise it up to pressures and temperatures by these compressors. In reality, it's not a compressor. It's a centrifugal fan. They call it vapor fans. And each fan is going to give you a level of temperature, like about 20 degrees Fahrenheit. So you start adding 20 plus 20 plus 20 plus 20. So you're adding wheels, maybe a step of 4 wheels, 6 wheels, 10 wheels. So they call it vapor fans to make steam. So like in brewery, many times we see the cooling side where they're doing a lot of cooling for fermentation and product and stuff like that, but they're also doing heating, again, for fermentation. And they doing steam to make hot water, and hot water goes for pasteurizer, get wash, clean in place. Well, the idea combination is that the heat of the refrigeration system goes and produce hot water for the heat pump produce hot water for where you really need hot water, and then flashes or sends hot water and flashes to an NBR, and NBR now makes steam. That way you don't have steam done by a fossil fuel, you're having steam done by a heat pump and an NBR. It's a combination of two technologies. The COPs on these technologies, combination of the heat pump and combination NBR, can get around 3. Think always this is a 2-stage heat pump in a way like that. So combining with NBRs, you can get around 3 total efficiency, not the heat pump on the low side or the heat pump on the high side. The NBR here can get an efficiency of 6. The heat pump can get here an efficiency of 5 or 4, but the total energy that you input and everything may be only a COP of 3, which is better than any technology around today in heat pumps with all refrigerants, or better than the boiler. So what we're seeing in the US, we've seen that US is 10 years back from Europe. We have about 250 or 300 cases of heat pumps in Europe. Europe has been ahead of US for a long time, basically because their gas prices are higher, so they need to find different ways of doing heat. Just the war between Ukraine and Russia just triggered the sales of heat pumps for the last 2 years in Europe. Germany didn't want to rely anymore on the gas line coming from Russia, so they needed to find different ways of heating. So Europe has been developing heat pumps for a long time. That's why we are bringing technology that is already proven, it's being tested, and it's been there for years, for transition now to the US, but manufacturing that in the US. We manufacture things in York, Pennsylvania. The spark spread is higher in Europe, reason that justifies more for the heat pump, but also they have something that is not yet in the US, is the tax on carbon emissions. A lot of cases in Europe are defined by the amount of money saved on taxes rather than on the energy. US doesn't have that yet. There is a lot of conversations by DOE and Congress and everything about taxing the carbon emissions in the US. Maybe that helps to trigger more sales in the US, but maybe not. Some companies may say, I'd rather walk away from the US and start manufacturing somewhere else, China, Mexico, where they probably don't have tax carbon credits. Europe has more funding, or they fund a lot of heat pumps more than the US. A lot of Europe is more district heating than process heat. I'm not saying there's not process heat, but they rely more on district networks, something that is not big in the US and Canada. Canada could be the second place for a lot of district heating, but US doesn't have that much. US has more district cooling, but not really district heating. So a lot of heat pump cases has been more around district heating than process heat. Europe has learned to move from steam to hot water, so they really invested in that retrofit that I mentioned. The only funding in the US today is the IRA Act and the 48C tax credit on any electrification, which includes the heat pump. The other thing that we see is the lack of understanding of heat pumps. Many people don't really understand what is a heat pump, capacities levels, temperature levels, and also how to integrate it into the process. Integration is key, otherwise the heat pump is not going to do their job. The lack of consultants, energy consultants, contractors, how to integrate heat pump into the process. The cost incentive integration is really high. Sometimes the retrofit, brownfields, how we call it, retrofit, so plants may run into $4 million on the retrofitting from steam to hot water, and then the heat pump may be about $1 million, so now you're around $5 million. It's too expensive. Management probably will be really hesitating about doing the project today or in 2 years because they want to see how that 5 million payback becomes in 2 years. The average we're seeing in the US for the paybacks because of low gas prices is 7 years to 10. Something that doesn't fit to a lot of corporations. They want to see 2 or 3. That's not going to happen with heat pumps. They need to start changing their mindset around the paybacks. Gas prices are still low in the US, so nothing we can do about it. Is more related what Congress or utilities do about it. So there's a lot of conversations between government and utilities and organizations, how to utilities become part of the game, how they can help end users, where they provide rebates, they provide incentives, they provide a better pricing structure, something else that they can help how people in the US really start jumping into electrification. Lead time today on heat pumps is somewhere around 40-50 weeks, depending on manufacturer. Who holds the line a lot is the heat exchanger manufacturer. Remember, you need to have these heat exchangers rated for that refrigerant, high pressure, and hot water. So it's not any heat exchanger guy. It has to be someone that is quality proven, has been on the market. So the good ones today, which can make heat exchangers, they are holding the line because they can only manufacture as far as 20 to 30 weeks lead time. Once we get the heat exchangers, we start doing a heat pump, it takes around 40 weeks, 50 weeks from our end. Think for a moment that everyone jumps into the heat pump or electrification. The current grid that the US has today is weak, is old, has not been revamped, so may fail if everyone starts jumping into that. So there's also another conversation about Congress, how they can revamp the whole grid in the US if everyone starts electrifying. So the cost of the heat pump, heat pump may cost $1 million, but the installation may cost a ratio of 3-to-1, 4-to-1 on the full integration, replacing heat exchanger, recovery heat, replacing steam lines to hot water lines, and that's a big problem, and it's related to the spark gap ratio, how much you get on that utility cost and your installation cost. So the average payback is 7 to 10 years. Another one we see a lot is the space restrictions. Many people have this engine room where you have all the equipment that provides utilities to the plant, like steam, like air, like heat, like cooling, and they thinking about seeing the heat pump in that same energy room, and many times they don't have any more space. That's one issue because the heat pumps are big, they're not really small. So it comes to the conversation where you want to sit this. Heat pumps has to be seated indoors. You cannot sit it outdoors, just taking like rain and sun, because if you do that, heat pumps are gonna fail. So you need to make an enclosure. So another way of making a solution for sitting them outdoors is you need to put an enclosure. What you see on the picture is an enclosure of heat pumps, right? Because the customer didn't have any space. Well, we see that a lot on the cases that we get from the US. There's a lot of space restrictions on many plants. Last one, a lot of heat pumps, they're not able to turn down to 0%. And you don't want heat pump to start, stop, start, stop, start, stop. That's pretty bad for heat pumps. You're gonna destroy the compressor. So you don't want that. So you have to have a way of handling partial load capacity. Even the compressor can run partial load, like piston compressors can go really down to 30%, like a screw compressor technology as well. You need to have a way of handling the partial load, the best way of putting a water tank. So people call them thermal energy storage. Basically, it's a water tank. You can call them a buffer tank, or you can call them a certification tank. So you feed volume, a fixed volume from the heat pump to the water tank. You don't want variable flow. That's going to create issues on your heat exchangers and heat pump. You want a fixed flow. And then you can put a variable pump from your water tank to your users. That way you can handle from 0 to 100% capacity, and you can handle any sudden changes, any peaks, anything where the heat pump doesn't see that. That way you have a more stable operation. That way you can have a better COP, longer COP, better operation of heat pump, less maintenance, many things. So the integration of the water tank may be something really high on cost because it'll be based on the amount of water that you need to storage. So you think that you want to storage 1 hour without a heat pump, or 3 hours without a heat pump, or a whole day without a heat pump, that's going to increase a lot the capital on the water tank. So that's going to increase a lot the installation of the heat pump, whether it's heating a building or heating a plant. Thermal storage is always needed. Last, solar projects that we've seen in the US, we start selling heat pumps about 2 years. It's taking a year to manufacture them and deliver them. But finally, some are already installed. Now some are in phase of commissioning, some are already running. We got some brewery cases, some dairy cases, and some district heating. That's as far as the reference in the US. Like I said, it's new in the US, so the reference is really short, it's not really big. We go to Europe, we go to Asia, it's quite big. But we come to North America, Canada, US, it's kind of pretty small on the reference because it's something that people are doing today because of decarbonization targets. So we have a 1.7 megawatt on a dairy plant, we have a 4 megawatts on a dairy plant, and we have a 4 megawatts on a district heating energy system. And there are a couple other ones on the way, on the pipeline. This one is a concept where they have water tank, heat pump, and electrical boiler. The four big. So you still need a way of making steam, that's electrical boiler, but you may need that electrical boiler when the heat pump goes down for service maintenance. Remember, you have to shut it down and do service on them. So you need to have a different way of making that hot water. Or sometimes the compressor may fail and then you need to find a way of producing heat. So you need to have a steam boiler some way, or don't get rid of your old boiler. So you never get rid of the boiler. You still have to have it. Some people, like I said, raise temperature with a heat pump to a low temperature and use an electrical boiler to finish the temperature. So you always have a need of the boiler no matter what. You never get rid of that. The question will be whether you want to go hydrogen boiler, biomass boiler, or electrical boiler. That's my presentation. Thank you, everyone.
Thank you so much, Ramon. That was excellent. Love all the case studies, and the video was great too. So we are a bit over time here, so I'm gonna pause it on the Q&A for now, but both presenters kindly included their contact info, and we'll also be sending this recording out. So definitely feel free to follow up if that's okay with the presenters on any questions you might have, or getting in touch. Clearly, there's a need for some more demonstration projects in the US and to kind of disseminate learnings from these early projects. So yeah, definitely hoping this technology will continue to take off and help decarbonize the industrial sector. So yeah, thanks again to Herman and Raj. Massive thanks to everyone for attending. And yeah, my colleague Shannon will be sending out the slides and recordings. So you'll have this to pass along and be able to review the slides if you wanted to zero in on some of the important information that was shared today. Thanks again, everyone, and have a great rest of your week.